Okay, so the last piece of this parametric week that we're doing is connecting parametrics to vectors through a vector equation. So you have that basic equation right there. You can see it on the slide where x, y is the position of an object after a certain time t. So this t represents time. And then that x naught, y naught is your starting point or your initial point, however you want to think about that. And then this AB, notice the brackets, that is your vector representing what the direction and speed that you are moving. So we put all these together, and the reason this connects with parametrics, as you can see, we essentially have like two equations happening at once here. We have our x equation, where we have x plus t and a, and then we also have our y equation here. Maybe not the best way. T and b. So we really could look at this as like x equals x naught plus ta, where y equals y naught plus tb. So it just shows you that it's connecting the idea of vectors to the idea that there's a horizontal movement and a vertical movement. So we'll work through this example together. It starts off where at time is 0, we have a is at 2, 1, so that means this is our initial point. So our x naught, y naught in the equation. And then after 3 seconds, b is at 5, 10. So notice, we're going to want to figure out how it moves at every 1 second for the equation. This just gives us for 3 seconds difference. So if we want to visualize it, we could also do a little graph here. Let's see, x has to go out 2, 3, 4, 5. 1, 2, 3. Not the best drawing. You guys get the idea. So a is at 2, 1. B is at 5, 10. So this object is moving from A to B as time progresses. Again, this is a 3-second difference. Okay, so part A says, find the vector representing the velocity of the object. So we want to find the pointed bracket part of the equation. Well, we can relate this back to just finding a component vector or a position vector back a couple weeks ago where we did the terminal point minus the initial point. So we want to do b minus a to tell us the movement. So let's see, b is for x, 5 minus 2, 3, 10 minus 1, which is 9. So we know our vector is moving 3, 9 in 3 seconds. So if we want to switch that to be in 1 second, well, we just divide everything by 3 to get us to 1 second. So if we divide each thing in the vector by 3, that tells us our velocity vector here would be 1, 3. So that's how much this point moves every 1 second. So now we could use that if we want to find the speed of the object per second. Again, just a little side note for vectors. This is part B of that example. Remember to find speed. That would be magnitude or length. It was just square root 1 squared plus 3 squared, which would be root 10, whatever that gets. So that just tells us the speed of the vector per second. So now, that was just a little side vector reminder. So now part C is where we're going to actually write this vector equation. So our vector equation, we have everything we need. Our xy should be there, because that's the whole point, kind of like a y equals equation. X naught, y naught is our initial vector, so that's a, 2, 1. That's where the object starts. And that, didn't mean to do that. Plus t, that's our variable. And then we have our velocity vector, 1, 3. Technically, those should be pointed. Google Slides does not let me do that super easily. So that's our equation. xy equals, we start at 2, 1, and then for every second that passed, we add 1, 3 to it. That means. So now part D says, use the equation to find where we'd be after 7 seconds. We're just plugging 7 in for t. So when t equals 7, well, 2, 1 plus 7 times 1, 3. Just follow order of operations, and then we'll add our corresponding parts. So 2, 1 plus 7, 21. Essentially what that means is after 7 seconds, we know the point will move 7 horizontally, 21 vertically. But then we know it started at 2, 1, so we have to add that to it. 2 plus 7 is 9. 1 plus 21 is 22. So that's where the point will be after 7 seconds. Okay, this last piece now brings us back to parametric equations. So let me switch slides so we have some space and rewrite this equation. Plus, whoops. Okay, so this piece is just a matter of separating it out. So if we want to write it as parametric equations, we can write x is equal to 2 plus 1 times t, so t. And then y is equal to 1 plus 3t. So here's how they connect to parametrics. We can write it all as vectors, or we could write it in this two-equation parametric form. So that's part E. And now the last piece says, use the parametric equation above. When does the object cross the line, and what is the point of intersection? Well, that's kind of a fun little connection. We want to know when it crosses this line. Well, notice we have an x, we have a y, we have an x, we have a y. So we can plug those in, and then we'll be able to solve for t. So our x is 2 plus t, plus our y is 1 plus 3t. Because if we want to know when it crosses that line, that means we want to know when they all have the same x, y points. It's just like a system of equations. We're essentially doing substitution with equation 1 and equation 2. They were just in different forms to begin with. So now we can just solve this like a normal equation, because notice we're down to one variable t, and that's our whole goal, is to find that t. So distribute, get our t's together, 15t, 6 plus 4 is 10, subtract that to the other side, gives us 62, divide that out, and we get to t equals 4.5 seconds. And that's it. So really this combines vectors with parametrics with basic rectangular equations, pulling them all together. So hopefully that helps. It's just kind of a nice little comparison to end this vector parametric week. On the worksheet, there's a couple of those for you to try on your own, and also just the answers to this one if you want to try it on your own without the video, are on that next slide. So, let me know if you have any questions. As always, you can email me, happy to answer.